In this video, I am going to explain the concept behind the correlation and how we can implement the correlation in Matlab. So let's start. So here we'll consider only the discrete time correlation, not the continuous time. Okay, so as the course is of digital signal processing, so we'll consider only discrete correlation. Main objective of this course or the video is to understand the concept behind the correlation and make a program or function, in a Matlab, to perform the proper correlation along with the time index calculation. Now, as we know, the correlation, it is a measure of the degree to which two different signals are similar. That means how much similarity is there in between two discrete time signal. Okay, so the correlation of two signal is basically of two types. One is cross correlation, another one is autocorrelation. So cross correlation means the correlation between two distinguished or two different signals, and autocorrelation is the correlation of itself. Say x of n is a signal, y of n is another signal, then cross correlation means it will find a similarity between x of n and y of n. That means cross correlation is in between x of n and y of n, whereas autocorrelation of, say, x of n means the correlation of x of n along with the x of n. Okay, both have the different applications in signal processing, communication, etc. So to start with the cross correlation, it is also, in terms of the mathematics, it also known as a sliding dot product or sliding inner product, the vector inner product. Okay, the cross correlation between x of n and, say, y of n is given by this formula, this tau xy. It is denoted like this. The suffix xy means, this suffix xy means the correlation is between x and y, taking x as a reference signal. That means the shifting will be done on y. So tau, or in some books you will find it as r. So correlation signals. So summation over minus infinity to infinity x of n, y of n minus k for all k. For all k, that is 0, plus minus 1, plus minus 2, like that up till infinity, that is minus infinity to plus infinity. Here this k is your shift, or also called the lag parameter. Okay, the order of the subscript, as I mentioned, indicates that x of n is your reference signal that maintain unshifted, which will not be shifted in time, whereas the sequence y of n is shifted k units in time with respect to x of n, both in the left and right. Now suppose if we would like to do the opposite one, that means if we would like to fix y of n as a reference and to shift x of n, then the correlation has to be denoted as, say, tau y of x of k. So then it is y of n instead of x of n first, then x of n minus k. Mathematically, which is also equal to, instead of y of n, we can write y of n plus k and x of n. So mathematically this is equal to this. Okay, so y of n plus k into x of n for all k. Now suppose k is 0, that is for 0 lag, then tau xy 0, if we put 0 here, then tau xy 0, if we put 0 here, then it will be x of n into y of n. Similarly, here also if we put k 0 here or here, then it will be x of n into y of n. So therefore, for 0 lag, tau xy 0 is equal to tau y of x, yx 0, and is n is equal to minus infinity to minus infinity to plus infinity x of n, y of n. Now if we look at or compare these two equations, so tau xyk and tau yxk, we'll find that tau xyk is equal to tau y of x minus k. Okay, that means something your even symmetric. Okay, where tau y of x minus k is nothing but the folded or the time reversed version of tau xyk about the origin k is equal to 0. Now if we compare it with the convolution, in convolution is commutative, that is convolution of x and y is equal to convolution of y and x. But here it follows the correlation between xy, that is tau xyk, is equal to correlation of yx, that is tau yx minus k. So point to be remember here. Now if we will go back to equation 1, this equation can also be written like this y of n minus k, x of this equation 1, y of n minus k can be written as y of minus within bracket k minus n. Okay, so then you can see this y is being folded first, okay, then shifted. So therefore we can write it as like x of k convolution y of minus k. So what does it mean? It means if we do the folding of y first, then do the convolution, is same as that of the correlation. Okay, so if we see here the correlation, since the summation is over n, in case of convolution if you compare it, then here it will be n and here this will be k, and it will be x of k, y of n minus k. That means in convolution first y has to be folded, then shifted, then multiplied, then summation. But in correlation, as it is k here and n here, okay, and x of n, y of n minus k, that means there is no folding. So it is as compared to convolution, the steps where first is the folding of y, then shifted the folded y and multiplied with x and take the summations. But in correlation there is no folding, so directly shifting the y and multiplied with x and then take the summation. So in convolution, folding, shifting, multiplication, summation, but in correlation it is shifting, multiplication, summation. Now from looking at this, before doing the convolution, if we fold y then do the convolution, then it is, because folding again, first we do the folding, then after that in as a first step of the convolution again folding. So folding, it is again same. So therefore if we do the first folding of y then do the convolution, then it is correlation. So correlation is essentially the convolution only, but before that you have to do the folding. So from this equation we find that the correlation process is essentially the convolution of two sequences, in which one of the sequence has to be reversed or folded. Okay, so this is the correlation between two signals, cross correlation between two signals. Now coming to the autocorrelation. So the autocorrelation of a sequence is the correlation of sequence with itself, as I mentioned. The autocorrelation of sequence x of n, which can be defined like tau xx or tau yy, whatever. Okay, so x correlated with x. So obviously x of n instead of y of n minus k, it is x of n minus k. So as like in this, we can write y of n plus k into x of n if it is yx. Now since it is xx in case of autocorrelation, so we can write it like x of n plus k into x of n. Now if we compare with this, it has 0 lag, tau xy 0 is tau yx is 0. So similarly here, tau xx 0 will be xn into xn, that is x square of n, which is nothing but the energy of the signal. As we understand, that summation over all time n x square n gives the energy content of the signal x of n. So zero lag of autocorrelation is the energy of the signal. Remember this. Now while computing the correlation, the mathematical steps involved, as I mentioned, first x of n and y n are available, then without folding. In convolution, the next step was the folding, but here without folding, directly shift y to the left by n, that is to make y of n minus k. Similarly to right by k, y of n plus k. So, sorry, shift to the right. This is right by n to make it y of, here it will be k, to make it y of n minus k. Slide y of n minus k to the right over x of n index by index, and then multiply overlapping sampling or overlapping weights of indices and calculate the sum. Carry this process unless y of n minus k slides all parts of x of n. Then similarly it will be shifted left. The value of the sum will be the correlation between x and say y of n. Okay, this is how we do the calculation in Matlab or in any mathematical computation of correlation between two signals. Now properties of the correlation, cross correlation as well as autocorrelation. Considering say two different finite time or finite energy signal, finite energy sequence, which is an aperiodic sequence, x of n and y of n. Now say let us consider their linear combinations. That means a1 into x of n plus a2 of say y of n minus k, where y of n minus k is the shifted version of the y of n, where a1 and a2 are any two arbitrary constant, and k is the time shift or the time lag. So then, as for the basic knowledge, we can calculate the energy of the signal as we know the energy is the summation for all time of the squared of the signal. So here the linear combination is a1x of n plus a2y of n minus k whole square is the energy of this linear combination of the two signals. So now just use simple mathematics, that it will be a1 square x square n twice a1 a2 x of n into y of n minus k, then a2 square y square of n minus k. Now from our previous calculation we have seen this summation over n minus infinity to infinity x square of n is nothing but the tau xx of 0. Twice a1 a2, it is, this part is nothing but the tau xy of k, and this part of course the tau yy of 0. Because it is y square n minus k, it will be y square of n. So tau yy of 0. So that means that the energy of this linear combination is the energy of the signal x, energy of the signal y, and the cross correlation between x and y. Okay. Now since the xn and yn we considered as the finite energy sequence, so therefore the energy E of the signal, this a1 x1 n and a2 y of n plus a2 y of n minus k is also finite. That means this is the total energy. So this total energy is also finite, that is something greater than 0 or equal to 0. Now coming back to this equation which is tau xx of 0 is the x square summation over x square n. Okay. from equation that we find that the tau xx0 is the energy of the signal x of n. So therefore this part, that is ex is tau xx0, similarly uy is tau yy0. Then that means this part is ex and this part is your ey. Now suppose this equation is being divided by a2 square. So then a1 square by a2 square tau xx0 twice a1 by a2 twice sorry, here it will be twice a1 because it is being divided by it is a2 a1 only. Twice a1 because it is being divided by a2. Okay, it is being divided by a2 square, sorry, since it is a2 square it will be a1 by a2 only, a2 square, sorry. So since it is being divided by a2 square, so it will be twice a1 by a2 tau xyk and plus tau yy0, which is greater than equal to 0. Now let us consider a1 by a2 as say m. Okay, so let us consider a1 by a2 as m. Then it will be m square tau xy0 twice m tau xyk and tau yy0. Now this equation, this part can be related with in a matrix form as this: the matrix m1, then this tau x of 0, tau xy of k, tau xy of k, tau yy of 0, and m1 which is greater than equal to 0. That means this is just the matrix representation of this part. Now, so any for a finite value of m, this part, this inner matrix, this is equal to tau xx0 into tau yy of 0 minus tau xy square of k, which is equal to 0. Okay. Now, since from this we can have this tau xy of k as the square root of tau xx0 from this only. Okay, tau xy0, tau xx0, tau yy0, and as we know this tau xx0 is nothing but the ex and the tau yy0 is your ey, so therefore it is square root ex into ey. That means the magnitude of the cross correlation function is nothing but the square root of the product of the energy between two signals x and y. Now if x is equal to y, so then it is tau xxk is equal to ex, because it will be ex into ex square, so ex. And of course it is tau x of k should be less than or equal, because it is exx, because it is here greater than equal to 0, so here it will be tau xx 0 will be greater than according to this, and which is ex. That means this equation 7 represents or implies that the zero lag of the autocorrelation sequence, this is the zero lag of the autocorrelation sequence, attain its maximum value, which is the energy maximum value. Now if we do the normalization with the maximum value of the autocorrelation function, so this was your autocorrelation function, and if we do the normalization with its maximum value, that is tau square root of tau x(0), then this whatever be the normalized one is called the correlation coefficient, autocorrelation coefficient. Similarly, the normalized value of the cross correlation will be your tau xyk divided by square root tau x(0) into tau y(0). So this rho is the correlation coefficient. So tau xy of k is all known as the correlation coefficient, and according to this we can find that mathematically the value of this correlation coefficient is always in between -1 and +1. If the value of value is 0, that means any value of rho xyk which is 0 means there is no correlation. There is no correlation. And if the values are towards 1, or say equal to all values are equal to 1, then it is highly correlated. Okay, highly correlated. Now with an example I'll show how to do the correlation. Now since already we are familiar with the convolution, and here in this process of correlation we find that the correlation is essentially the convolution, but before doing the convolution one of the signal has to be folded. So then since we are familiar with the convolution, then what we do is we can evaluate the correlation through convolution. For that we need to do the folding first. Suppose let us consider two sequence, x of n is say 1 2 1 1 and y of n is 1 1 2 1. Then to do the correlation, what we do is x of k 1 2 1 1, that y of k 1 1 2 1, then we fold y of k, which is, if we fold this, it will be 1 2 1 1. Then do the convolution. So here I have done it in a tabular method. Hope you understand. Already you know the tabular method of the convolution. So here it is your x of k 1 2 1 1, and this is your y of minus k 1 2 1 1. Then do the tabular method of convolution. So 1 into 1, 1 into 2 2, 1 into 1 1, 1 into 1 1, so like that, 2 into 1 2, 2 into 2 4, 2 into 1 2, 2 into 1 2, like that, and then do the summation. 1 2 plus 2 4, 1 plus 4 plus 1 6, 2 plus 1 plus 2 plus 1 6, 2 plus 1 plus 2 5, 1 plus 1 2 1. So 1 4 6 6 5 2 1 is the finally your cross correlation between x of n and y of n. Okay, so this is all about the correlation. As I have shown here, the properties, while doing the properties of this correlation, we considered the x of n and y of n as the finite energy or simply energy signal. Similarly, we can do the evaluate the properties in case of the periodic signal, that is the power signals, that is finite power signals. Just little bit manipulation of this mathematics. Okay, hope you understood about the correlation. Now we'll move to the lab work in Matlab, how we do the correlation. So by reading out the pre-lab document, that means up till this, most of us, I mean all of we have understood or to get the idea about the correlation, but that was how we can perform the correlation mathematically. But in this lab handout in the following section, we'll explain how the correlation is done in Matlab by following that step-by-step procedure. Now in Matlab there is a built-in function called xcore for evaluating the correlation. So xcore, xy or a, b, say, we'll find out the correlation, cross correlation between a and b, and xcore x will or a, say, find out the autocorrelation of a. So Matlab provides a built-in function x core say x comma h, which will compute the correlation between two signal x and h. We'll take an example. Before that, let us look at the functions available in the Matlab. So x core function, which is the cross correlation function estimation. Okay, so suppose C is equal to x core a comma b, where a and b are say length m vector, means the row vector or a signal. That means A is also having m numbers of signal, B is also having m numbers of signal. If both are not of m numbers of samples, that means the length of A and B are not equal, then this function itself will make it equal by adding extra 0 at the rightmost. So where A and B are the length of m vector, obviously m greater than 1, it returns total number of samples in C as twice m minus 1, as it is the case in the convolution as well. If A and B are of different length, the shortest one is 0 gated, as I mentioned. It is being done by x core, you need not to do beforehand. And C will be a row vector if A is a row vector. If A and B is a column vector, then C will be a column vector. Now if instead of AB, if we pass only one argument A say, then it will be the autocorrelation, where A is the length of say m, returns twice m minus 1 autocorrelation sequence of sequence C. Now the zeroth leg, as I already have seen in the mathematically in the properties, the zeroth leg of the output correlation is always in the middle of the sequence at element m. So it will make it always at the middle, this particular x core. Now similarly, if instead of say A as a row vector, if A is a matrix by say m by n, of course m greater than n 1, then it returns a large matrix of twice m minus 1 row and n square numbers of column, containing the cross correlation or the autocorrelation sequence for all combination of the column A. The first n columns of C contains the delays and the cross correlation using the first column of A as the reference. The next n columns of the C contains the delay and cross correlation using the second column A, and so on and so forth. Okay. Now along with that, here I forgot to mention, along with that, this C means this x core function, along with this C, it also returns the lag vector, the shifted vector. Okay, so for example, if x is equal to 1 to 1 1, so that same example, as I mentioned, it also returns the lag vector. So x core x comma h will return this. Okay, so which is the lag is minus 3, minus 2, minus 1, 0 is always at the middle, then 1, 2, 3. Now there is a problem. Okay, the problem is this lag vector is not essentially the time indexed vector. If it is at 0 and 0, obviously this is not your time vector or time indexed vector of the resultant signal. It is always the lag shift. Okay, if it is a different time index, then this x core will not return. I mean, this x core y will be correct, but this lag will not be equal to that of the time indexed vector of the resultant signal y. Okay, so therefore we need to have our own program to find the correlation. So here is another example. I'll come to this example later on. Okay. So as I mentioned, there is a problem with the built-in function. The xcore function assumes that two sequence, as like this convolution, it begins at n, assumes that both the sequence begins at n is equal to 0. So this function, as like convo, CONV convo function, it also, this xcore also neither provides nor accepts any timing information if the sequence have arbitrary starting points. So what is required is the beginning and the ending point of y, that is time index vector, for a given finite x of n and h of n. Okay. Now it is easy to determine these points using Matlab. Okay. So here I'll show you in the Matlab the first part. So here I am considering x of x as 1, 2, 1, 1, and say h as 1, 1, 2, 1. Okay. Then say PQ, P will be your correlation vector and Q is your lag. This is x core within bracket x comma h. So this is 1, 4, 6, 6, 5, 2, 1, as I have shown here. 1, 4, 6, 6, 5, 2, 1 with minus 3, minus 1, 0, 1, 2, 3. This is this minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay, so here is no time information. The as I mentioned, convolution correlation is essentially the convolution with folding of h. So let us do that. Let us check that also. H of 1 say is equal to, in Matlab there is a built-in function to fold the vector, which is flip LR. It is flipping left to right h. So you see h was 1, 1, 2, 1. So once we flip it, it will be 1, 2, 1, 1. Then I am doing the convo CONV in between x and h1. So you will see the same result. 1, 4, 6, 6, 5, 2, 1. 1, 4, 6, 6, 5, 2, 1. That means otherwise you see CONV x comma h is different. So it was the convolution. This is your convolution, but this is your correlation. Why? Because h1 is the folder of h. Then do the convolution. Okay. Now we'll go to develop. We are going to develop our own Matlab code for doing the correlation, in which I'll explain detail as like I did it for the convolution, a detailed code, step by step procedure of the detailed code. Okay, detailed code for the correlation. Okay, so this is the code. So this is the code. You know already, CLC clear all closure. Now already it is in our practice that whenever we take some signals, the important is the first starting time index, then the signal values. Say nx1 is your enter the starting time index of the input signal x of n, then the x is the signal values. Now if nx is greater than 0, that means suppose you are not starting at 0, not even starting at some negative index, but rather it is positive. So it is always a good practice to start at least from the 0 by adding some zeros. If nx is greater than 0, suppose you have type 2 nx1, that means your signal originally started at 2, but in practice will start it from the 0 by adding 2 zeros. Okay, at 0, 0, at 1, 0, then from 2 your actual signal starts. Then Lx, it will calculate the length of the signal and accordingly the ending time index Lx plus nx minus 1. And finally the time vector for the x will be nx1 to nx2. Similar is the case for the nh, I mean the h of n. Then how total number of sample in the resultant signal will be as like convolution. It is also lx plus lh minus 1. That means the number of sample in x, number of plus number of sample in h minus 1. That many samples will be there in your resultant signal. Now coming to the starting time index of the resultant signal. So it is the starting time index of the x minus the ending time index of the h. Why? Because in convolution, in correlation, there is no folding. Or in terms of convolution, if we think of the correlation as convolution, then first you have to fold the h. Now if we fold h, then the ending time of h becomes the starting time of the folded h. Okay, so then if we do the convolution, obviously as like convolution, starting time of x plus starting time of h is the starting time of y, resultant signal y. So like that, with reference to that in case of correlation, the starting time of the resultant signal will be the starting time of the x and minus negative, negation of the ending time of h. Obviously ny2 as like this. The ending time of y will be n plus the starting time. N is the number of sample, capital N is the number of sample in y, and y is the starting time, minus 1. And finally the time scale for y, resultant signal y, will be ny2, ny1 to ny2. Okay, so therefore with an example I am showing you. Suppose my starting time index for x is minus 3. So minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. And this is my the vector. Okay. And my nx1 is minus 3. That is the starting time. Length, as you see here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So length of x is 9. And nx2 is, you see, it will be 5. 1, 2, 3, 4, 5, which is nx1, which is minus 3, plus lx 9, minus 3 plus 9, 6, minus 1, which is 5. So nx, that time vector for the x of n, is nx1 to nx2, which is minus 3 to plus 4. Okay, sorry, plus 5. Similarly, the h of n, suppose I am considering h of n as nh1 as minus 2. So minus 2, minus 1, 0, 1, 2, 3, 4, 5. LH is your 8. And total number of sample here in h is 8. So and h2, the ending time index for the h of n is 5. And accordingly, the time scale for the h of n is minus 2 to 5. Now the total number of samples in y is lx plus lh minus 1. That is your lx is 9, which is the length of the signal x. LH is your 8, that is your length of the sequence or signal in h. So 9 plus 8 minus 1 is 16. And accordingly, the ny1, nx1 minus nh2, which is your nx1 is your minus 3, and nh2 is your 5, so minus 5, it is minus 8. And similarly, ny2 will be, capital N is the number of samples in y, plus starting time of y is ny1 minus 1, which is 7. So it is minus 8 to 7, the time vector for y. Okay, let us, up till this is okay. So let us run this. Okay, so here the starting time index of the signal x of n, according to this only I'll put. So my starting time index for x of n is -3, so I'm typing -3, then this signal only x of n, since it is a vector it has to be typed within a square bracket. And for h, the starting time is here -2, so -2, and the signal values are this. Okay, now see, once we run it, this is the signals x of n from -3 to +5. This is your h of n from -2 to +5. Okay, this is the signal. Okay, x and h. Now here no need to do the folding. So second part is directly the shifting of h, then multiplication and summation. So here again I have divided in number of left shift and separately the left shift and right shift. So first let us do the left shift. So how many numbers of left shift? So number of left shift will be the nh2 minus nx1, because the h is not folding. Okay, so the nh2 here, nh2, as you can see, nh2 is your 5, nh2 is your 5 minus nx1 is your -3. So total there will be 5 minus -3, that is 8 numbers of left shift. 8 numbers of left shift. So let's see here, L underscore L is the number of left shift. This is 8. Okay, so I'm assigning that value to the k, so k is equal to 8 now. Now y L, for the left shifted value of y, I am considering a zero matrix where the values will be assigned later. Now for I is equal to 1 through k, or 1 through this L, so L underscore L, that is the number of left shift. So first what we do is the shifting. As we do shifting, we append 0. If it is the left shift, we append or add 0 at the rightmost. So it is HFS1, which is the shifted version of H of left shifted version of H. Okay, so suppose I is equal to 1, then it will be the values of h and 1 0 at the rightmost. So suppose I is equal to 1, so it is shifted by 1. That the time scale, of course, all these things is similar that we do in the shifting, already we did in the shifting program. Okay, so this is the time scale for the shifted one, nh1 minus I to nh2. Then the multiplication, for multiplication, as we know, both the signal must have the equal number of samples. So how to make it? By adding zeros in both sides of both the signals. So this is how we added zeros in both the x as well as in the shifted h to make number of samples equal to 0. Number of samples equal to be equal. Then 1 is transposed, x is transposed, then multiplied will give you multiplication and summation. And finally plot each steps. So let's see. So there will be 8 numbers of left shifted. So each of n shifted by 1 towards the left, 1 0. Shifted by 2 towards the left, 2 zeros, like that. So these are all 8 numbers of shifting, left shift for the h of n. So this is this result. Then accordingly, if we see the resultant part, that is YL, Y underscore L is the resultant part, left shifted part of the resultant signal Y, which is 20, 56, 86, 55, like that. This is the values. These are the values. Similarly, for the right shift, same way, for the right shift, this part will do the right shift and calculate the resultant part of the correlation for the right shifted part of the h of n. Okay, and finally if we append both left and right, we will get the y. Now while doing the right, there is a point to be remembered, that zero shift means there is no shift. That is also considered as a shift. So that is why, as you see here, I considered I is equal to 1 plus the number of right shift. So number of right shift is nx2 minus nh1, which will be your 7 in this case. So I am considering 1 plus, 1 2 7 plus 1, that is 8, because it also includes the zero shift. So that is why while shifting, the first one is in this process it is I minus 1, so that when it is I is equal to 1, it is I minus 1 is 0, that means zero shift. So it is also considering zero shift. So as you can see here, the 7 number of right shift along with the 0, it becomes your these things 8 shifts. Actually it is h of n minus, it is not h of n minus 1, it is h of n. We will modify this part. In the x level, in the title, yes, should be I minus 1. You see, it is h of n minus 0, that is h of n only. So h of n minus 1, n minus 2, n minus 3, n minus 4 up till n minus 7. Okay, I'll save it. Okay, later on I'll put it here. Okay, I'll put it here later on. So the right shifted values, I mean the values of the values of the resultant signal due to the right shift is y underscore r. These values. Okay. These are these values. Now finally appending both is this. Okay, and the resultant time sequence ny is minus 8 to 7, minus 8 to 7, and this is your resultant signals. Okay, the same thing can be done with the x core. You see, your x is this, h is this. Now say PQ, P is your return signal y, Q is the lag, time lag, x core, x comma h. So you see the values are, you don't consider this minus 0 here. So 20, 56, 86, 20, 56, 86, 85, 117 this. So there are total of 17 samples. Minus 1, 2. But here we got total number of samples, capital N as 16. But here we obtain 17 because it always makes the always the zero lags at the middle. This x core function makes zero lags at the middle. So as you can see, our time scale was minus 8 to 7, but here it is minus 8 to 8, that lag, time lag, which is not the time index, which is time lag. Okay, as you can see, we have shifted 8 times in the left, so that is why it is from minus 8 in the time lag. You see L underscore L is our 8, and we shifted 7 times at the right, so that means your L underscore L underscore R is your 7 times right shifted, so that is why it goes up to 7, but here it goes up to 8 because to make it 0 at the middle it goes up till 8. So that is actually the difference in using the built-in function. If you use the built-in function, it does not return the time index of the correlated signals, rather it all gives the time lag during the correlation process. Okay, so hope you understood this code. Now thing is that this code is to explain the detailed procedure of your correlation. Okay, this code is for detailed explanation of the correlation process, but in practice you need not to write the large code, longer code. Okay, so we can make it simpler for particularly doing the correlation, as we did it same for the convolution as well. So this is the simplified code. So here I need to modify this ny1 from this and then I do is like this. So this code is done something like we did for the convolution, but here there is no folding. It's in a matrix form by making both x and h equal by appending or by adding zeros at the rightmost. So this capital X and capital H is the zero added version of x and h. Then do the matrix method. Okay, so if you run it, so same one, only I'll put same signal that we use for the previous one. Something is wrong here. Different programs actually I used, somehow something is wrong in this. Actually, I'm sorry, here this process is you are using convolution, this correlation using this is for convolution. Sorry, we'll use this code. This is using convolution. Yes, we'll do it. sample values of x of n. So this is my sample values of x of n, starting time of x of n -3, and then enter the sample values of y of n. So this one and starting value of -2. You see the same results, yes, 20, 56, 56, and it also use the same because I put it as 0 padding before, so therefore it also gives y core b. So the same one. So here what we did is x and h, this is the folding part. First we do the folding. This part is the folding of y, then this part is the convolution. This part is the convolution of x with the folded of y, and this is for managing the time. Okay, the result is this. This is your x, a, y, folded y, and cross correlation. This is also another program of similar type. Okay, need not to go through this. Now here I am giving the detailed code for the correlation. This okay. Okay, now the next task, making our own correlation. Making our own correlation functions, say for example. Now we can define one own function in Matlab that is slightly modified from the built-in x core function. So we'll use in our modifier function we'll use convo function as underlying function, but it will perform correlation of arbitrary support sequences. Okay, that you all know. First go to okay, so what we'll do is So I'll type it as my core. So what we'll do is, in this my core function, these are the argument x and nx for the time and the sample values for the x, h and h for the h. Now your how will we modify this? So what will be your ny? As we did it for this, ny1 is this. So which is your nx1? This is correct, but it has to be minus, instead of nh1 it will be the last time index of nh. So how will you get that last time index of? So that I'll get say here I am calculating Lx is equal to length of x, then LH is length of h, then ny1 will be minus nh LH. Okay, so ny2, as we know, this nx of Lx, just okay, simply we'll put Ly is equal to length of ny, oh sorry, length of y is not calculated here, so we'll make it shorter. Okay, so nx length of x and h plus length of h, this is your LH, and ny will be ny. Then before doing this you have to do the convolution, I mean before using convolution function you have to use your flipping. So hf, so folded of h, we can use flip lr within bracket h. Then in convo, instead of h you have to use hf. Okay, that's all. So or rather you can use x core also here, but then you need not to do this flipping, that you can use x core x comma h. Okay, so let us save it as my core. So this is, I'm going to use that my core my core function to calculate the correlation. So these all will be same. So then this will be my core. Okay, so I'm just saving it as correlation using my core. Okay, let us run it. So again I'm using the same one only, same example. Okay, now you see the y value is the same as my previous values because I have used the same examples. So this was my y 20, 56, 86, 85 like this. This one, and ny minus 8 to 10. Oh, sorry, something is wrong. Minus 8 to, it should be up till 7, why it is 8, 19, and y length of x 9. This ny1 must be nx1 minus nx2. So here nx1 minus this is okay. Okay, so here is the problem that in ny1 is okay. This the first value of nx and last value of nh, and the ny2 will be the total number of samples in y, that will be your lx plus lh minus 1 plus the starting time of y and y minus 1. Okay, then folding the h, then convo. So this will be your correlation function. Okay, let's run it. So then again I'm using the same one, so -3. This is the sample values for x, this is for h. Okay, now say y will be this 2056. As you can see, these are the same values as that of this, and ny is a minus 8 to 7, so it's correct. So this is how we do the correlation. So using designing our own correlation function, say mycor, this is the function that define, then this is our own defined function named mycor. Now we can use this function just as any other function in Matlab. So this is the program where this mycor function is called to calculate the correlation between two signals. Now this y of n will show both the values and the time index. Next task, for you need to consider x of n is this, h of n is also same. Actually you need not to consider both. Here we are going to find out you are required to write a Matlab code to find y of n as the autocorrelation of x of n. Plot x and y n in one window, and then label x axis, y axis, then applying it, and give the title of all the figures. That means you need to do the autocorrelation. You can use the detailed program of xcore, I mean the correlation. Also you can use the same function, that function that we define for the correlation, to find the autocorrelation. Now there is another one. This is task 6. So the task 6 is to find the correlation coefficient, as we discussed, and mathematical detail of this correlation coefficient. This row xxk, which is the correlation coefficients. This same correlation coefficient can be calculated in Matlab by using the function corf, corf, corf. Okay, so this will calculate the correlation coefficient between two signals x and y. So where x and y are the column vector, but even if it is not column vector, suppose x and y are row vectors, then also it will calculate the correlation coefficient by making them in a column vector. If x and y are not column vectors, then it will convert first x and y to column vectors, then it will do the correlation coefficient. Okay, so as I mentioned, correlation coefficient gives the similarity measure, and if the correlation coefficient values are 0, then it is non-correlated. If it close to 1, that means it is correlated. So let us see in our present case. So x is this, h is this. Now let's see correlation coefficient. Sorry, here it has to be within square bracket. So correlation coefficient here is 1. So let us do this. Transposing it will make it column vector. Both has to have same number of length. Okay. So there is one in each, one less. So let us put h is equal to h and 1 0. Okay, so then yes, that it is correct. Both has to be of the same level. So as you see, these two are 1, diagonals are 1. It actually gives the covariance, which is 1, and that means highly correlated, and these are slightly correlated, around 60% of correlated. Okay, so correlation coefficient gives this. To calculate the correlation coefficient, this function is used in Matlab. Okay, so that's all about the correlation. So you need to put it here: observation, comments, explanation of the results that you obtain. So you need to answer these questions at the end. Okay, and again in my next video I'll further explain this correlation related to some random signals, where it will be more meaningful, which will be applicable for proper signal processing or your communications. So here one thing I left out in this one, another example. So these examples I'll straight away explain in the Matlab. See, in this load noisy signals S1, S2, these are already add-ons in the Matlab. That S1, S2, there are two sensor signals, this is the noise signals. Then this Xcore will find out the correlation between these S1 and the S2 with the lagging vector. Then it will find out this I will be the maximum of the absolute value of the autocorrelation function. And the time difference, that is the lag of I, then the plotting. So this is your S1, this is your S2, this is the correlation, and it is zero lagged at the middle. Okay, this is a practical examples where we use the correlation for random signals. So here we have discussed detail about the correlation mathematically, what is correlation, cross correlation and the autocorrelation mathematically, and derived the properties of the correlation, and from which we derived the correlation coefficient, some examples, and then we have seen how we can do this correlation in Matlab using the Xcore function. Also we have written our own code and explained it, and how to do the correlation using convolution, and finally we have designed our own correlation function named as mycore to evaluate the correlation. Okay, and finally the correlation coefficient, how to measure the correlation coefficient in Matlab. Okay, thank you for listening.